everyone, welcome back. And now it's our last talk. Let's welcome Dr. Hyunseung Kang from University of Wisconsin-Madison.
Thank you. Thank you for the introduction. Welcome, and also thank you again for the organizer, Caroline and Ben, and people at the staff as well for actually organizing this and making sure this runs. Thank you again also for staying to stick to the end. So this talk will be on something that my student now Dr. Concharla worked on for about 2 years on how to do randomized experiments under privacy constraints. So this is something that I just go through the overview of this talk. So the idea came actually in some this part. Actually, the talk is organized this way, but the way we got the problem was actually in the bottom up, where I was kind of frustrated that we weren't able to get individual level clinical trials data. And it actually takes forever to get these things. And even if you get them, you'll only get summary statistics of them. And in fact, for better transparent scientific replication, it's important that we actually have these individual level data so that not only can you build different models, different machine learning models at the top of it, but also to combine experimental data so you get more power out of it. So then also coincidentally, our stat department wanted to have a different way of evaluating online courses at the same time, and tasked us to actually come up with a way to evaluate courses, but that still protects student privacy, specifically student educational records. Those are protected under FERPA. And so given those, we thought about this for a bit, then we came up with a design that actually estimates causal effects under the constraints of privacy, specifically differential privacy. A lot of you might be familiar with this. Berkeley kind of, stat department Berkeley has kind of really took this off to a different level. And so that's the idea. How do you construct randomized experiments under constraints of privacy? So we're going to review a couple concepts that might be familiar to some of you, not all of you. Some of them. One of them is local differential privacy that's common in CS and stats. The other one is something called non-adherence and cheating that actually we borrow ideas from experimental psychology. These psychologists actually have a very clever way of testing whether you're a cheater or non-cheater. So we kind of take this and take it to a modern level. And then we combine these two simple ideas with sample splitting to come up with RCT that's also differentially private and can consistently estimate the ATE and do inference as well. There's a nice theory here, but I mean, I think theory can be nicer than nicer. And one of the things that we are kind of wanting to explore in the future is the trade-off between efficiency, relative efficiency, and how much privacy we're losing by doing these kind of experiments. Okay. So just to review, the gold standard to unbiasedly estimate the ATE is usually the RCT, where you randomly assign a treatment A to individuals and you observe the outcome. Typically, the best way you use some people to treatment, some people to control. This is the ideal case. And if you take the difference in means of these things, these are unbiased estimates of the ATE. Now, these are used a lot in education, health, tech, A/B testing, social sciences, you name it. This is how it's done, and if you have the resource to do so. But one of the implicit assumptions that's in an RCT that's not even covered in the SUDVAs or the positivities or the condition ignorabilities is that the participant that's participating in the trial is actually going to be willing to participate in the trial and also give true responses to their treatment. So what if that response is very sensitive in nature? So the other one would be, what if the PIs, myself included, or maybe the clinical trials folks, wanted to actually share their data about some cholesterol drug or something to the public, and so that they can actually not only replicate, but also combine these data to even conduct more powerful tests. And some of these responses are actually protected by law, and some of these things are FERPA, which is the one we're more interested in when we did online education, when we ran our trial. But HIPAA is the for health data, and GDPR, all the cookie, accept the cookie, don't accept the cookies that you see in your Chrome browser. That's for, and it depends on which country you're into actually. And then California has its own version. So if you actually notice, California, there's its own version of GDPR. And some examples of these sensitive responses include the more famous example about voting that Facebook done, where actually they've merged people's voting records with these voting buttons to see how the impact of having these friends on whether you actually participate in voting. But the one to your left is that what we actually did, which is what is the effect of actually having an instructor present in a Zoom session while they're lecturing on the participation rate, test scores, and all these other things. That's one of the things that the department was interested in learning. And in both of these cases, the response here could be, here was educational outcomes, and here is voting records should ideally be private. Okay, that you don't want to share this data, that people don't want to share their GPAs or test score results. And so how do we do science, transparent science, while guaranteeing privacy? That's the question that we're trying to tackle today. Now, we're not the only ones we looked at this. There are many ways you can kind of tackle this question. And so we draw out this very diagrammatic way. On the y-axis is maximizing data privacy. On the x-axis is essentially maximizing scientific value, replication. You can see the individual data. You can toy around with all the data collection you wanted. And so on the top right axis here, if you don't ever run an RCT to get science, you maximize privacy. You never even have to collect data in the first place. That's not often the case. So oftentimes, most of the spectra in practice lives here, where people only share the summary stats, or people actually only give you aggregate responses. So this is summary level responses, and there's also some literature in the database world on how to aggregate them properly. And then on the other end of the spectra is maximizing scientific value, where you run the RCTs, don't care about the laws, share everything, and then hopefully you have honest science. But then people don't want their clinical trials data to be out in the world. So the problem is that most of the current world lives here, around this middle area where you share the aggregated information or share de-identified information. But the problem is, probably the people in differential privacy know this, it's actually fairly easy to, reasonably easy to de-identify the de-identified data set. So re-identify the de-identified data set by actually through data merging. And there's a famous example by Sweeney, I think, in about 2000, where they were able to identify the people from Netflix, anonymized data from Netflix, by merging a couple of things together. And so that's one thing. The other thing from a statistical angle is that the trade-off between how to do inference while guaranteeing privacy is not actually clear. So this is just a diagram. We're not explicitly laying out how to quantifying how this trade-off occurs. So what our approach, or this design, is an RP-RCT, robust differentially private RCT, that actually not only is that rough, we think it would work at this angle, but also quantify this trade-off in a relative sense. Okay. So let me just review two concepts to explain what RP-RCT is. The first one is differential privacy. So this one, some of you may be familiar with. We take the easiest example. This is not the first reference, by the way, of differential privacy. So the idea of differential privacy is take some true response, you put it into some algorithm, and it spits out a privatized response. Okay. So for example, if your true response is something, if your algorithm is always spitting out 1, that's perfectly differentially private. That means regardless of what your true response is, if the algorithm always produces 1, you can never recover back what the individual original outcome was. And that's called zero privacy, or really perfect privacy. The other end of the spectra is where the algorithm spits out the original true sensitive response all the time. And that's infinitely differentially private, or there's infinite privacy loss. And what differential privacy does, essentially, it quantifies this middle ground here at the two extremes. And this epsilon differential privacy is it's now actually adopted by certain tech companies. Apple adopts this for Apple Health data. If we ever use Safari, it also uses a certain type of epsilon differential privacy to send this data back to the servers to actually do studies. Or QuickType, the one that does your autocompletes as well. And then Google and Uber, I think, also uses this system to actually do science, to do A/B testing, while simultaneously guaranteeing privacy. Okay. So this is the formal definition. Some of you who have actually seen this literature probably are familiar with this, but the punchline is essentially some very, 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 very smart people quantified privacy by essentially saying, if I have 2 true responses, there's this algorithm such that this algorithm, the outputs of this algorithm are very, very similar, even though the true responses are very, very different from one another. So that's roughly what this says. And the epsilon essentially is a quantification of how different between those outputs are. Okay. So let me just give you an illustrative example, just from actually, this is what we use for when you actually ran this trial, DICE version of this. So suppose the question that we were interested in, the population quantitative interest, is whether somebody paid attention in lecture. So if, let's say, a lecturer wants to ask an online Zoom call, online lecture, whether you want to pay attention or not. So Bob's true response is that he never did. He was just sleeping. He turned off his video camera. He never actually paid a single thing about linear regression. Okay. Now, what the FR algorithm, so the differential private algorithm, does is it lets Bob spin one of this thing, and then if the spinner lands in red, Bob is asked to say no. If the spinner lands in green, the Bob is asked to say yes, and if the spinner lands in blue, Bob is actually going to respond honestly. Okay. And so in this case, the spinner lands in red, and Bob's privatized response that he reports to us will be no. And if the spinner lands in green, the Bob will always say yes, even though his true response was no. And what the key here with differential privacy, at least in this particular example, differential privacy, is that Bob knows this information. Actually, Bob knows this as well. But the investigator or the instructor only gets to see this response. And what the privacy guarantee is that I get to see a noisy version of a sensitive response. And that noisy version is essentially controlled by that essentially the area of that green, red, and blue triangle, essentially. In fact, this little exact proportion corresponds to an epsilon of 1.1. But if you actually maximize it this way, it corresponds to an epsilon 0.5. And notice that the blue area, where Bob must answer honestly, it gets smaller. That means there's less privacy loss. And if you can imagine as epsilon goes up, the blue increases, so there's more privacy loss. Okay, so higher epsilon, more privacy loss, lower epsilon, less privacy loss. Now, this you can theoretically just apply to RCTs and be done with it. But what we realized when we actually did this experiment is that people lie, students lie. Okay, and if you ever taught a course about certain anything, when they get excuses, not everyone lies, but at least one house says everyone lies. And what happened was as follows. So we gave this, and we thought if the Bob spinner lands here says no, Bob might actually not follow this instruction as advertised. And if Bob might say, maybe he doesn't want to say that he didn't pay attention in lecture to an instructor directly, or maybe Bob human nature wants to lie, irrespective of the question itself, or because Bob can lie, and he will lie. Okay. So what happens is sometimes that Bob will actually, even though the spinner landed in red, and Bob is supposed to answer no, Bob might actually say yes. Okay. And so he deviated from what we wanted him to do, and actually reports him a yes. Okay. Now, as the PI, I don't know from this whether he lied or not. I think he followed this, but then maybe he was lying in the process. This is a realistic problem that we face when you're actually doing this. And what we actually figured out is that there's actually a way to detect cheaters. So this is known as cheaters, people who actually deviate from the protocol by doing a very simple trick to DP algorithm, differential private algorithm. The idea is essentially instead of having one differential private algorithm, you have two differential private algorithms that are just slightly different. And then you just split the sample into two parts. And then you give one differential private algorithm to one group of people, and you give the other slightly different differential private algorithm to other people. And you compare the outcomes between the two. And by doing this, you can actually get how many people are cheaters, and you can actually debias your cheater estimate. So that's what this slide says essentially. And this isn't a new idea, actually. If you dig far back, there are some very, very clever people in experimental psychology who are trying to detect cheaters in a completely different sense. We just added a modern flavor by adding sample splitting, really. And that's also the classic idea, but just, this idea of sample splitting comes up frequently in recent days in machine learning. And that's the idea that we did, to detect this kind of deviation from Bob being a cheater and to know how that cheater, to decontaminate our scientific responses. We essentially gave we can give two different differential private algorithms and then get the responses and essentially measure the deviation between what we expect the number of yeses to be from what we observe. And that difference essentially amounts, that difference you can use to quantify the number of cheaters and then to unbias your estimates. And so, yes?
Hypothetically, let's say everyone always lied, always
yes.
This would be able to detect that.
No, so if everyone cheats, and we want to be like an ATE estimate, right? If everyone says no to yeses, then there's no way to scientifically even get what we wanted to say. So actually, we're going to talk about identification that counts on proportion of cheaters. But,
also,
yes.
clarification, the cheating is allowed to depend on red, green, and blue.
Yes, the cheating is allowed to depend on red and blue, but cheating is not allowed to depend on the treatment. So we'll talk about the specific identification. So this is our RP-RCT. It's two simple ideas just brought together with some sample splitting on top of it. So the idea is we enroll people, in the case students, and we randomly we collect the pre-treatment covariates, and there's an art to that, by the way. We randomly split the sample, so we randomly subdivide the students into two groups. One group gets one particular spinner, the other group is another particular spinner. We then randomize the treatment within each of these subgroups, gather their outcome data, and their treatment assignment, and the S is what sample you're in, and then all the external covariates. What we don't get to see is where the Bob spinners landed, their actual response, whether they're cheater or not. So the investigator only gets to see some privatized, noisy version of the response, the treatment assignment A, the sample split, where the sample were, and then the covariates. Yes?
Do the students see the proportions or they only see the color?
They can see the color or proportion, and they can cheat based on those proportions as well. What's critical here is that they cannot cheat based on whether they're assigned treatment or control. So that's a big assumption that we have to make to actually get ATE estimates. So we'll talk about the plausibility of that assumption in our case, but yeah.
So what's the treatment then?
Treatment here is actually, we'll talk about it at the very end, but essentially whether you have an instructor face present in a Zoom lecture versus instructor face absent. So this is one of the questions that our department wanted to ask, is whether whether the instructor should turn on a video while they're lecturing versus whether they can turn off the video and audio is sufficient. Okay. So compared to an regular RCT, how does it differ? One of the two, we just had 2 steps. One step is to essentially this random splitting part we have to do initially. And the other part is to add the differential privacy algorithm in between. But beyond those, the regular step remains the same as before. And here's the specific algorithm, the parameters we use. But the key thing that we want to prove, and the first thing about this algorithm, is that this algorithm produces differentially private responses. Whatever response we get, it's differentially private. Now, the key here is that we only can guarantee differential privacy among non-cheaters, those who actually follow the algorithm. If they don't follow the algorithm, let's say decided to let's say they were trying to be clever and they give always the opposite of the true responses. By differential privacy, you can design an algorithm where it can actually detect it backwards. So what we can guarantee is that if you decide to truly follow the algorithm, we can guarantee differential privacy. But if you decide to be clever and cheat, somebody might be able to actually discover what your true response is. So that could be something to advertise when you actually do this response. Okay. There's also properties of differential private response being immune to post-processing and all these other things. But yeah, essentially the idea is that I can give you a differential private response and you can do all kinds of processing on it, but you won't be able to recover back the original response. So that was proven by Dwork, and it was summarized in this book here. Now let's talk about identification. So we guarantee that our data set, our response to treatment is differentially private. What about the identification of treatment effects? So in a typical RCT, we typically assume these things: stable SUPA, the treatment is randomized, and the positivity overlap. This will be satisfied in the RCT, and it will be also satisfied in our case. And then if you do this, you can identify this by, again, the difference in means between treatment and control. Now, what the RP-RCT also satisfies by design is that the random sample splitting happened, that we initially randomly sample split, that we actually, the spinner is randomized. So we can actually, the spinner runs at random. They can choose to react to that spinner how they want, but the spinner itself is random. And then the random is, this is just to formalize things. This is that the treatment was randomized. That's at the end of the day. Okay, so those are also satisfied by design. Okay. Now the 2 things that we have to assume, in addition to these, what we call satisfied by design, are as follows. The first one is that the cheater's response to the investigator is independent to the treatment assignment, conditional on the splitting variable, the spinner variable, and whether the spinner landed. So essentially, once you have these variables, the cheaters are not trying to change the response to the investigator. If they got the treatment, they might respond differently. Maybe they got the control, they might respond to something else. Okay. Now, this will be plausible if the treatment is blinded, or if the 2 people don't react differently in different ways. But this is not plausible if the treatment is definitely unblinded. So this is some of the things that we have to, a heroic assumption that we have to make identification possible. The second one just says that there's some honest people in the data set. And so that's just, we have to believe that there's hopefully honest people in the data set. Okay. And so if those things are possible, then what we can show is that we can identify the treatment effect among honest people. Okay. That is that this tau H, which is treatment effect among honest people, can be identified by this formula here. And the proportion of cheaters can also be identified by this little complicated formula here. Now, just to give you a sense of what that result means, suppose that the entire data contains all honest participants. That will mean that using our RP-RCT, we can actually identify the ATE while guaranteeing at the same time differential privacy. In contrast, the usual RCT would just be able to identify the ATE, but the outcome itself is not differentially private. Okay. Now, let's take the case where all of them are cheaters. There is not a single honest person in the study population, so that would be a very pessimistic view of the world. And if that's the case, then there's no way that an RP-RCT or let alone an RCT can actually identify a scientific quantity of interest. So that's the other end of the spectrum. Now, in between, there's some honest participants and there's some not so honest participants. And so in that case, RP-RCT identifies 8 amongst the honest participants and guarantees and among those honest participants, guarantees differential privacy. And actually, if you think about this a little bit carefully, and I worked in IB for a long time, this is actually very similar to local average treatment effect among compliers in the sense that I can't identify who the cheaters and the non-cheaters are, but I can identify the proportion and I can identify the treatment effect among the non-honest folks as well. So actually the identification result actually is there's a lot of parallels between those 2 assumptions. Now, once you're able to identify, there's estimators doing this. So under the RCT, that's the estimator. Under the RP-RCT, essentially it's the difference in means estimator just divided by some proportion of cheaters and the spinner ratios. And if you do this, you get an asymptotic normal estimate. You can do inference, and you can also estimate this quantity consistently, the variance quantity consistently. Now, the more interesting part was how much are we losing by using an RP-RCT? We're essentially injecting additional noise to the outcome to guarantee privacy. And so we're going to be losing a couple of efficiency characteristics. And so this is formula that my student took a while to derive, but essentially characterizes how long it derives it. But the key idea is as follows. This ratio between the two variances of the R estimate under the differential private data versus the the regular RCT where the outcome is not private is going to be growing based on the number, growing as monotonically increasing as a function of the privacy loss parameter epsilon. Okay? And only when the privacy loss is infinite, where do we get the same variance estimate? So essentially we get that. So we're always going to be losing some amount by actually adding some noise to this thing. Now, there's been a question about, at least in our, when we are dealing with and when we're designing the experiment, how do we actually go about specifying this epsilon quantity? So this thing, you have to know a couple of things. Once you know this formula, you can kind of have a tolerance for how much relative efficiency you're losing. The other thing is whether these tau 0, tau 1 is the effect estimates, and they're the control and the outcome that may be informed by subject matter experts. There's this power analysis that people might do in a clinical trial that you kind of have to assume. And then the recommended data privacy standards that may not exist currently, but hopefully will get standardized, and even in clinical trials if this hopefully gets adopted in the future. So in our trial, we set epsilon to be 2, which is matching the Apple Health data. Yes?
What is lambda equals 3? Remind me what lambda equals 0 means?
For
any
so this is I'm honest, folks. Because the thing is, if there's some cheaters, then the RP-RCT identifies the slightly different quantity than the RCT actually. So the efficiency characteristics doesn't make sense because the biases are not different. And so when they're all honest, we still wanted to know, okay, I don't know if they're honest, but let's assume if they're honest. If I run an RP-RCT versus an RCT, how much are we losing by injecting an additional? So that's why the efficiency characteristic makes sense in that case. That's an apples to apples comparison. Any other questions? Okay. So additional thing that we done was we realized that we're going to be losing a lot of power. And so we need a covariate adjustment to make it more efficient. So we have a covariate adjustment estimator that actually is essentially an extension of the augmented inverse probability weighted estimator that some of the talks mentioned. It's estimated when consistent, even if the outcome model is wrong. So it's a nice way to do this. And actually, what's more important is that actually you need to ask the right kind of covariate questions to actually improve efficiency, something that we realized when we're actually designing this trial. Okay, but there is an estimator and the exact formula is in the paper. So let's get to the actual trial. So it's rare for a statistician to actually collect data and actually design, collect, and go through the entire process. And my PhD student apparently was one of the few students in our department that actually went through a trial collecting the data below to analysis and methodology development. So thankfully, we were tasked with this task of how do you assessing the quality of online lectures that went, many of Berkeley probably included, MIT included, and other places, probably a lot of the courses went online. And there were some questions about what's the most effective way of delivering lectures online. And so one of the things that we did was one question that we studied was whether turning on lecture video cameras was effective, or does that change learning outcomes at the end of the day? Okay. Now there are prior studies that suggest that students pay attention, more pay attention if the instructors are present in lectures, and if compared if they're not. And unfortunately, when you actually want to get this data, it's all locked up and there's no way to actually get the individual level data. So this is a problem, and there was no way to replicate it in order to combine the data sets so you can get more power. So what we do is we use an RP-RCT to test this hypothesis. Does having instructors present in lecture, online lecture, improve attention versus not having that lecture? And so we ran this literally about a year ago, recruited undergrad students, and then we recruited 72 students. We set the epsilon to what Apple Health, at least when their white paper released, to be their health standard. So we think it's fairly private. And we can also publicly share this individual level data. So you can see their individual outcomes, all the covariates of the assigned. And in fact, this took a lot longer, convincing the IRB that we can actually release individual level, educational level data set. But they were able to, thankfully, I actually also want to thank the IRB officer for actually going through the process of explaining differential privacy, what that means, and how that impacts in science and clinical trials. So what was the actual trial? So this is essentially my graduate students. We were lecturing them about RCTs. So there's a little pun there, where one of the students in the control arm did not get to see my graduate student. And the treatment group, the student got to see my graduate student talk about RCTs. Okay? And they're about 37 or 35 in each group. Covariates are balanced. The paper goes into details about the fact that it was randomized to do. And then what the FR did, the spinner, was essentially my graduate student learned JavaScript and actually wrote this code where the student will roll the die. And then based on how the die lands, it could either answer yes to a question, always no, or answer honestly. Okay. And so the student actually, we told the student a priori about that there could be a die that's in the process. And so that's, and these die probabilities are set so that the privacy loss is exactly 2. Okay. And so the results. So one of the questions that we asked is, did you find it hard to pay attention to lecture or video on RCTs? Okay, and you did yes or no. And in fact, using our RP-RCT, which guarantees differential privacy, we found that as expected, if students find it easier to pay attention when there's an instructor present actually speaking to them rather than some voice just speaking to them at RCTs. In fact, we can get the confidence interval for this. And then we also estimated 24% cheaters. Okay, so now everyone's honest. Okay. And this all results also agrees with previous RCTs without using the differential privacy characteristic. Yes?
What scale is that?
Sorry?
What scale is it? Percent? That is, or
Oh, this is in percents. Yes, thank you. Yes, so 31%. So relative differences in proportions. Yes. Thank you. And yeah, again, just to make sure that the data is differentially private, and so individual level data can be shared for replication or data fusion if you wanted to combine multiple RCT styles and to actually get more power. Okay, so this is a summary of our paper. So we provide a new experimental design, robust private RCT that guarantees differential privacy while allowing estimation of causal effects. One particular cool aspect about this design is it's robust against cheaters who might deviate from protocol, and we're able to detect these cheaters and correct for that bias by using the sample splitting and using a slightly 2 different DP algorithms to actually detect this. Okay. And the RP-RCT can estimate the ATE among non-cheaters. There's also doubly robust estimators for this. And then we found through actually running this trial with 78 samples, so it's not a big sample, that we were actually able to detect that people in having your face on a lecture is actually helpful in getting the students engaged. So maybe this is a takeaway. I don't know if it generalizes to every university, but hopefully it could be something that could be useful. Okay. There's also trade-offs between relative efficiency and privacy that we explored. There's some future directions that my current students are working on, efficiency bounds, how to optimally design differential private algorithms. So there's an entire work on local differential privacy, getting feedback to actually optimize these things. We're trying to figure out the easy way to actually convince the IRB officer that's also differentially private versus just a spinner being differentially private. And then better ways to estimate this cheater proportion. Currently, we're using a Lagrangian way to do this, but I think we can actually, if there's possible to predict cheater status maybe by certain type covariates, it could be helpful. So we're not currently including we're not using covariates to predict cheater proportion of cheaters right now. We're just doing it by just simple difference in means. Yeah, just wanted to thank everyone involved. It took several PhD students, the entire department's administrative staff, and convincing many instructors to help us and to tailor these questions, how to properly ask these questions. So really want to thank the entire UW-Madison staff department for a junior faculty trying to run this trial and then getting this out, and also helping my graduate student to do so. And also Mike Bioki for some advice on how to tailor the IRB process. Okay, and thank you for your attention.
Thank you. Let's move on to the panel discussion. And so the 3 speakers